My admittedly short, yet extended period of programming, I have been hard-pressed to find a programmer who doesn't prefer to work at least as much as they can in the command line. And I think there's a few endemic reasons behind this. For instance, programmers prefer to work with the keyboard, given that we do so much typing. Introducing another input device seems just silly and inefficient. At least that's my opinion and the opinion of many others. There's obviously things that go against this. But I think that there is a certain aspect to the shell that lots of people have discovered, yet certain people haven't, that it introduces so much more efficiency into your work because you are getting the machine to work for you rather than you working for the machines. Sounds like a Rage Against the Machine talking point, but it is true. We invented computers effectively out of laziness so that they could do things for us. And the shell is a perfect example of how we have managed to design something where we get the machines to do work for us. And so this is basically me on the behalf of lots of people who have discovered these features already, kind of throwing down a ladder for the people who are still stuck at the bottom of the tree trying to get up, who haven't yet discovered some of the more intriguing features of the shell. And some of these are so insignificant it might seem like it would never be useful, but then once you start using it properly, then you'll start to realize that these are some of the most life-saving features in the world. So, the first thing I'd like to talk about is the humble cd command. So, given no arguments, cd will cd you into your home directory. Very simple. cd also provides you access to two directories, or actually, there are two directories in every directory which are actually logical. They're not real, but they can be used as though they were real directories, and these are ... and . The directory is the current directory. The ... directory, if we ls ... we can see the users on this system. If we ls ... we can see the files in my home folder. The folder is useful when you need to provide a local path. For instance, if I compile the test.c binary, if I just type a.out, you can see that it can't find it because it's not in path. But if we run /a.out, we can see that it runs. In the same way that if I was to go into the home folder and run ethan/a.out, we get the same result, as the dot is simply being substituted for the working directory. The ... directory is incredibly useful as it allows you to traverse backwards up the directory tree, but I see it being used inefficiently very often. For instance, to get to the root, I see people often go cd.ls, cd.ls. People forget that because ... is simply just a logical directory inside every directory, you can simply do cd.out/. It can be used just like any other directory in the tree. For instance, if I go into Hobbit and then UI components, I'm working on, I don't know, the list component, discovered a bug in the scrolling code yet again, and then I need to test it at the root. Well, rather than going cd ... cd ... to get to the root and then running make, instead I could simply run cd ... I'm going to show an example now. For instance, say I need to get back to a directory which is in the projects directory, or even in the programming directory, let's say. I need to get to a directory that's in the programming tests C directory. Well, instead of going cd ... cd and then you can write a semicolon, we'll come into that in a minute, cd ... then cd ... all in a row, and then finally cding into the correct directory. You can instead simply write cd ... //tests/c/ low level, or is it linking? Let's do perf. And then we have specified a path which will be implicitly expanded to where we want to go. You don't have to only use one ... at a time. This is a perfect example as well to show off the second most useful feature, in my opinion, of the cd binary, and that is the cd dash. We can see that when I ran cd dash, it printed out a path and moved me into this path. Let's see what happens if I type it again. It's moving back to this directory again, and it's printed it again. So if you run this multiple times, you'll notice that what it's doing is it's swapping you between these two directories. If I cd to my home folder by just typing cd, and then I cd dash, you can see that it's going to swap us between these two directories. If we actually read the man page of cd, we can see that a special case is given for cd with just dash, and if we can find the relevant section somewhere, this shall be equivalent to the command cd and print working directory. It changes to the previous working directory and writes its name. So what this can be used for is to quickly switch between two directories that you're doing work in. For instance, if I'm working on test.c, I don't know, maybe we want to indent these with a tab, go back to pop it, look in main.go, you can see that I just switched between two far vastly removed directories in my file system tree just by using cd dash, because it seems as though the designers of the shell realized that very often we like to interchange between two directories very quickly, or we like to temporarily change to another directory. For instance, say that I'm going into dsjs CLI, and I'm going to go into source, and then conf, and then I'm going to edit the conf.c source file. This here relies on a utility function called path concat, which will perform a static concatenation into this buffer here, mfn. So I could use gd and vim to go to this definition, or what if I need to edit the source file around it? Well, let's ack for path concat, and let's give ack the path dot so that it can do the whole source, and we can see that path concat is defined in file io.c. So let's go into //util and let's vim fido.c, and then let's look for path concat. Okay, we can now find our bug. I don't know, fix bug here, and then we can just cd dash to get back to what we were working on in here, because what this can be used for is to temporarily change path to something else that we are going to use just once. I'm going to type cd with no arguments again to go to my home directory, and now I want to talk a little bit about shell globbing, because shell globbing is probably one of the most underused and yet underrated features that the shell provides. And I should note as well that most of the things we've talked about so far are POSIX compliant, so even on a shell like dash, you can still do this. You can see that cd dash is still working perfectly fine. It feels like a bashism, but it's not, because the POSIX designers are slightly smarter than it seems when they design sockets. So, shell globbing allows us to match any path name which matches a certain pattern. And a very common mistake that people make is that they think that these patterns are regular expression patterns. They are not. In fact, if we look at the man page for shell globs, they explain that it is not the same as a regular expression. They say it somewhere, I can't remember, it's note regular expressions. Wildcard patterns are not regular expressions. Shell globbing is far removed from regular expressions in that there are some functional changes. For instance, this question mark is functionally equivalent to the regular expression dot character, and the star is equivalent to a regular expression dot star character. And these brackets or character groups are equivalent to extended irregular expressions. But without having to know what all of that means, let's take a look at some examples. So, when you type a star, you're basically seeing that any list of characters can go here. So if I type ls, this is the same as typing ls star, apart from the fact that all of the things in that list that match it will be given as arguments. So if I type ls star and then use a bind to auto-complete it, we can see that it's filled in every single directory in the folder. Let's say that I want to get all audio files, star.mp, star.mp3. Well, you can see it's matched the Doom soundtrack in here that I can now play. And let's say I want to match all source files, for instance. Let's go into programming, project, CLI source, let's say file star.c. We can see it's detected the two only C source files. But let's say I want to match all C files and all header files. We can see it's now found us all C files and all header files as well, and detected they're all C source files for the file command. And the other type, I'm going to use cd dash again just to prove the point. The other type of character that you can use in these glob patterns, apart from character classes, which will match any of the characters within them, and the star, which matches anything at all, is the question mark. And this says that you can match any single character here. So, for instance, I'm going to if I make some files, I'm going to make the files 1234.c, and this is just for an example, and I'm going to talk about those bracket lists in a minute. But when I've created these files, each one of these has a certain beginning. But let's say as well that I create main.c. Well, if I ls star.c, we can see that it's going to find us all of the files that have the C prefix. But what happens if we want just a single character .c? Well, we can use just the question mark character. What happens if we just want two characters before the .c? So touch22.c. Well, we can see 22.c was not matched. Will it match this? Yes, it will, but it will not match any of these, as they do not have two unknown characters. And so whenever you want to match any character or any explicitly sized group of characters before some known item, you can use a question mark. So I think there are features in things like Microsoft Excel that have a similar notation to this, and I think actually in I think it's SQL, when you have SQL-like commands, where you do select star where name is like, select star where name like, and then you can do like, I don't know, Ethan question mark Marshall. So this will match my name, and it will match Ethan K Marshall, it will match Ethan A Marshall, but it will not match Ethan Atkinson Marshall or something. That would be an invalid match. It wouldn't match that. So the question mark simply matches any single character, the star matches any string of characters, and anything inside the brackets is a group of characters that can be matched. And that's the basics of shell globbing. The main thing to grasp is that they are not regular expressions. These are the only features that they have. Some say it's limiting. I have never met any situation other than listing out dot files, which would be useful to have a beginning anchor for. But other than that, I have never met a situation where shell globbing has let me down. So I'm going to go back to the globbing directory, and I'm going to remove everything in here using a glob again, just to prove the point. Say yes, and I'm going to show again the command I used a minute ago to show this bracket command example as well. And as I was doing that, I also used command reverse searching, which will be the next topic, in fact. So all you can see here is an example of a shorthand initializer. This is in fact equivalent to this. All that we've done is we've substituted the things between the commas and then placed it at the end. And you can do this multiple times. For instance, I can do 1, 2, 3, 4 dot C and H. And we can see that it's going to create 1.c, 1.h, 2.c, 2.h. And so each of these, it will calculate every possible permutation between each of these. So you can create marvelously complex things. For instance, I could do 1234.c.h dot test, or if you have a comma and then nothing, that means that there can be nothing there. So I could do, for instance, maybe I could do HPP for creating C++ equivalents, and we can now see that we have 1.c, 1.cpp, 1.h, 1.hpp. And so we can see that we're starting to create enormously complex patterns that can be created just by talking about all the different possibilities. So you can create multiple possible examples of things by simply placing them in the brackets here, and the shell will expand this into the argument list after you have typed it. So let's tackle a problem now. That problem is the fact that we often type the same commands over and over again. And for me, for instance, this might be git init, it might be git status, it might be git reset hard. All of these commands are incredibly common, and so as a result they end up being stored in the history file many times. And my shell is actually configured to store every command once, but have a separate file that stores references to commands that were done, and then the history file actually sorts the commands by how recently they were typed. And this allows the reverse search, which on my shell is done by pressing Ctrl R, to search through the commands that I've recently typed and to substitute the ones that I've used the most often. For instance, make and sudo make install. And so all that you're doing when you're typing a command like this is you're doing a reverse search through your entire shell's history, and it will substitute out a command for you. Now, I think in Bash you can do the exact same thing with Ctrl R, and it will do similar to ZSH, which is my shell. And all that you do is you begin typing out the command. For instance, git reset hard I use quite often for distributed git management through emails, for instance. And so rather than typing out the same command over and over again, instead you can just reverse search it by pressing Ctrl R, and you're really getting the machines to do work for you. A feature that people often underestimate is the feature of an alias, because not only can you have aliases in your shell command files, in your shell startup files, you can create temporary aliases or change aliases temporarily while you're working on something. So for instance, if I am working on my program podbit, the go build command requires you to be at the root of the file system tree, or sorry, the make command, which calls go build, requires you to be at the root for environment variable reasons. I can't just use go build, unfortunately, because it requires this for cgo to work, but I have created a shell function called cdr that will detect the root of the file system, or the root of the git files tree, and it will cd into it. So what I could do while I'm working on this is I could make an alias, which is cdm, an alias cdm to cdr make. So if I go into UI components, list.go, and I don't know, let's fix this bug again, and then cdm. We have cd'd into the root and we have run make. The only problem that we now have is that we are now at the root again. So let's change up our alias and let's cd dash. And hopefully this will work. There might be some problems to do with the way that the cdr command works, but components, and let's revert this change that we just made because we obviously didn't actually fix the bug, and then cdm. There we go. So the use of aliases for temporarily, and then you can unalias it once you're done. The usage of aliases in order to make your life easier when doing specific tasks is an extremely powerful feature of the shell. Now, in the beginning, when I was talking about creating multiple directories at once, or moving through multiple directories at once, I showed the example of ce ... semicolon cd ... semicolon cd ... And I don't properly explain this, but this brings us onto the topic of shell error handling and command chains. And this will also lead us onto the topic of pipelining, but I'll leave that for later on. But every command that's under Unix, and actually under Windows, although it's disguised from you very cleverly, has an exit code. So for instance, if I start up my podcast client and then attempt to run it, we can see that we get an error saying that it's already running. So this command exits with a status which is not 0, or a failed status. This command here, if I exit it, will in fact exit with a 0 status, because the command exited successfully. If I run podbit again, we can see that it exits successfully. So we can actually detect this to do kind of pseudo error handling, and to get the shell to do things for us based on whether commands succeeded. So, if a command succeeded, and you type at the end of it, this will tell the shell, if this command succeeds, then run this. So what I'm going to do is echo and then some random text. In fact, let's make it success, close it. We can see that success has been echoed at the end here. The inverse of this is the or operator, which says, if this command failed, then run this. And we can say that it did not echo success at the end. If I open the client in the background again and attempt to run it, we can see that it's done success here because it failed. This or here says run podbit, or if that failed, run this. Then there's also the neutral way of doing this, which is, regardless of the exit status, just run this afterwards, and that's a semicolon. So regardless of whether podbit fails to run or whether it runs successfully, success is going to be printed. And so the semicolon is the kind of neutral equivalent of these. So you can chain together long sequences of commands that all together decide whether you're going to run another command afterwards, and you can use this to do some one-line automation. So for instance, ping. So let's say, for instance, you want to try and download a file, but you're not sure whether you have internet connection. Maybe your bar has disappeared mysteriously. So what we could first do is we could do ping and then -c, it tells us the count. Let's take it to do it once, and then let's ping an IP that's basically always up, and we can see that ping transported 64 bytes. So because ping succeeded, we can put an at the end, and we can say curl http 1.1.1.1, and we can output that to 1.html. And let's run this command now, and we can see that both commands have run, and if we actually look at 1.html, we can see that we get a Cloudflare notice for some reason. But the point is that the second command has run because the first one succeeded. Now this brings on to another interesting topic of subshells. As you might notice here, that if we actually run this and we do an OR at the end, the shell will interpret this as being if this curl fails. So, if the first command fails, none of the stuff that comes after it will attempt to run. And this could be a problem, because what happens if we want to print an error message? Well, what we can do is we can tell the shell to spawn a subshell, and this subshell groups together these commands in a shell instance and then does something else depending on whether that succeeds. So we can then echo something else at the end, and we can see it's going to do the Cloudflare again. If I disconnect from the internet, device Wi-Fi, and then disconnect WLAN 0, we can see that WLAN 0 will disconnect. If I then run this command, we can see that the first command will run in a subshell, and then the second command will execute because the first one failed. And this is how you can have order of operations in the shell. The penultimate thing I want to talk about is how you can get the shell to do maths for you. So there are certain programs like calc that you can get to do for you, or BC-L, which does basically the same thing as calc but worse. And both of these are perfectly good options. I in fact have an alias for BC-LQ where I just press mod F1 and it will open up a quick calculator in the corner for something that I need calculating. For some reason when I did this I actually needed a calculator to do 6 times 90. But when you need to get the shell to do this for you and assign it to a variable, you can actually use this operation here. You can do double brackets, I think actually it's brackets like this, and you can place the mathematics that you want it to do, 10 times 20, and assign it to a variable, and then echo $A. we can see that it's done the calculation for us. 10 times 20 is 200. As you can see by the errors I was making, I don't use this very often, mainly because of my calculator bind that I have here, but this is very useful if you're writing shell scripts. Something that's also very useful if you're writing scripts are variables. So variables in the shell are stored persistently for all of the time that your shell is running. So for instance, if I have a path like my Go path, this is actually stored by the Go runtime at my startup. So it's in Go root, I think, or is it Go path? Yep, and we can see that it's been set to my Go folder where I install all the modules and put the source code for Go projects. So this is a variable that's been set and exported, but not all variables have to be exported. A minute ago I created a variable called A, which I can reference with $A. So variables in the shell can be assigned by simply creating a name and then putting afterwards what you want to assign to them. And this can be either arbitrary text, I can do this, or it can be the output of a command, for instance. And it's important to note as well that if the output of the command could have spaces in it, you should quote it. Double quotes interpret the $signs and also commands inside of them. Single quotes do not. You can see the highlighting doesn't show it interpreting it. But for this purpose we don't need to. I'll just put quotes here in case. And set A equal to ls-la. If we echo out A, that should be $A. We can see the output of ls-la is outputted. So this is how you can assign to and use variables, and these can be used anywhere in the parameter list. For instance, if I do unique and then I give to unique, and this is the triple input operator, we'll talk about that next, I give it $A, then unique is going to operate on this input data. So you can assign variables just setting them equal to. They can be set to any data type, including raw numbers, and you can access them using $sign and then the variable in quotes. And even you can create kind of pseudo aliases this way. So for instance, if I do bcat equals bat, and then I do $bcat, and then we can see that it's actually run the bat executable, which is just a simple syntax highlighter. You can also reassign variables to any value or to no value at all, and it will simply be set to nil. I said a second ago that we were going to talk about file redirection, and while we're talking about file redirection, I think it would probably be very useful to talk about standard in and standard out and piping. So pipes in Unix take advantage of the fact that input and output through programs is done entirely using blocking file I/O streams, and I'm going to talk about that in the C tutorial series, but for now all that we need to know is that input is served into one file and output is put into another file. One of those files, two of those files, output and standard output and standard error, are combined together and put into the terminal, and standard input is simply a file that goes to the program. And so by default, standard input is just all of the lines that you type in your shell. So for instance, if we type cat, normally the cat program, if we look at its POSIX manual page, says that it will concatenate and print files and shall write them to standard outputs, and that is what you can see on the screen. So if you just run cat with no arguments, you'll be surprised to learn that it doesn't actually error. All it does is it connects the standard in to the standard out, and so you can see that when I type a line, it appears in our standard out here. The cat program, however, also uses standard error. So for instance, if I tell it to cat, and then in Unix, when you type just a dash, that means standard in, and then I tell it to concatenate a file that obviously doesn't exist, then I type in standard IO, and then in Unix as well, when you press Control D on your keyboard, that's an end of file, we can see that cat says ASDF no such file or directory. This is being printed in standard error. And so we can actually get the output from a program and store it to a file using just this arrow here. And so we can type now into this program, if we do test.out, and I'm now going to type, this will appear in my file, hello world, type Control D, and we can see cat ASDF has still appeared here, but the rest of our output, as from before, has not appeared. Why? Well, because the output from this program has now appeared in test.out, because the standard out of this process was set to test.out. And this is a very, very clever and very, very elegant way of handling input and output, in my opinion. So you can get the output of any command and arbitrarily output it to a file, but you'll notice that our standard output here has still appeared on our terminal. That's because standard error was very specifically designed to separate itself from standard output, because errors are not part of the main program's output that need to be seen by other programs, and we'll see that in a minute when we do pipelining. They need to be seen explicitly by the user. So unless the user explicitly wants to put error messages in their output file as well, the user is just going to see these. If you want to output error messages for any reason, what you do is you type 2, then an arrow, and then test.error, for instance. This will now overwrite the file, and it's important to note that when you use this dash here, it will overwrite and truncate any file that you put here. Any existing contents will be permanently lost. So you should be very careful. We look at test.error, we can see that our error message has appeared. It's important to note as well that you'll notice that no output from this command has appeared whatsoever. This is what I typed in. Not even the error message has appeared on our terminal, because the error message went straight to this file, and the output went straight to this file. Now, but what happens if we want to output both of these to the same location? Well, in certain shells, what you can actually do is put an @ sign here, and this is implicitly the same as outputting these to the same file, but this is quite verbose to write. Because this is so verbose to write, I should say. But unfortunately, this is not POSIX compliant, so if you use this in a shell script, it will actually not work, it will error. The POSIX way of doing this is to do @2, and then this @1 here says at the location that this goes to here. It means send this to file descriptor 1, redirect to file descriptor 1. And in fact, we can do this with standard in as well. We can actually redirect standard out to standard error. So if we do this same thing again, we can actually, these are both now appearing in our standard error. So if we were to pipe this into another program, xargs error echo would work better. We can see that actually this is appearing only from our cat here. We're not getting any output whatsoever from the echo program, because our standard error is not going to this here. So that is how file I/O redirection works. But I was going on about other programs seeing the output of files. What was I talking about? Well, what I was talking about was pipelining, probably one of the most cool features of the Unix operating system. Pipelining allows you to connect the input and output of multiple programs together in a line where the data flows from left to right between each program as it sees the data. This means that you can use multiple different programs to operate on the same piece of data, each of which makes a little change about it. And you can also take data from one source and you can pass it into another way of transforming it. So let's have an example here. If I curl wttr.io and https, I think this should be. Oh no, it's oh, because I've got my internet off. Yes, I'm such an idiot sometimes. If we cat out test.c, we can see the output of this program has appeared on the terminal. And so this on its own seems pretty useless. All we can do is look at the file, until you realize, actually, that this can be shown as the input to another program. And actually, it's often considered inefficient to use this as catting a program and passing it to another program. Can easily be replaced with a shell input redirection, or with simply passing it as the file operand. But what you can do is, this is just for an example mind, don't do this in practice, you can do cat test.c, and then we can pipe it into the program bat, which will syntax highlight it. And then if we set the language to C, we can see that bat is going to syntax highlight this correctly. In practice, we could just do bat-lc test.c, but this is much more efficient for longer processes. For instance, if we run ps-e, we get every process on the entire system here, and I'm not going to show it for long because it's got information about the system in it, but if we sort each of these by passing it into another program called sort, we can now sort these based on their process ID. So we can see the most recent process to be spawned was a kworker thread. Now, what happens if we want to extract one of the fields out of these? Well, what we can use is we can use awk. And awk is another program which allows for the extraction of fields, and what we can do is we can print $1, and that will extract all of the process IDs. Took a quick break there to get a drink of water because talking for so long, nearly half an hour, has made my throat hurt. But anyway, we were getting the PIDs of all of the processes on our system. And so this is an advantage as it allows us to pipe together a lot of programs that can all do separate things with this. And then finally at the end we can pipe it into a program like less, which will allow us to page through it, or even vim, which will accept it as input and allow us to edit at these PIDs. So obviously it starts at PID 1, which will be init, and then we can start adding notes, for instance, and you can see how we can create enormously complex things that would otherwise be done with a program. You know, the Windows way of doing this, for instance, would be to have a program called getPIDs maybe, and then you'd have to have a program like the task manager that does this for you. Instead, what I do is I just do this and then have these PIDs placed into a Vim instance for me. Very simple and nice. So before I move on to the actual final thing I'm talking about, because I've said I'm stopping at least twice now, I want to cover some of the final little complexities about file redirection that I realise I forgot about. So I talked about how to redirect standard out, how to redirect standard error to standard out, how to redirect both different files, but I completely forgot about standard in. So when we type in, we get them sent to standard in. But we can also send files to standard in. So for instance, bat send, let's set the language to C, and then send as the standard input file test.c. And we can see that it's read from standard in, and it's got this file as its input. And so this is a read-only copy, it can't actually change it. If we do, I don't know, like sed, and then just delete everything, sed is going to delete every line that gets passed to it. If we pass in test.c, it's obviously going to print nothing, but if we then bat out test.c again, we can see that it's all still there. All that's happening is each of the lines in this file will be read by the shell and will be sent to this process as it is asking for lines from this file. Another way that you can do this is often it's very useful to send a command some arbitrary data. So for instance, there's a program called tr that will allow you to translate between two character sets, so AB, FL, I don't know, AB, it will send it to FL, but often it's very useful to send this arbitrary input. For instance, so maybe you want to disguise your email address, like ab@ab.com or something, and it's going to disguise it very cunningly like this. What you can do is the triple redirect operator, and so what will happen is the shell will create a temporary file in memory, and then it will set it to the standard in of the process. And so the standard in will read whatever is between these quotes, hello world, AB, and the TR program is going to read it and it's going to perform its operation on the input passed between these quotes. And because these are quotes, you can do things like passing variables. For instance, let's say I want to translate between go and translate it to, I don't know, uppercase, and I'm going to pass it in $go path, and we can see that it's going to translate every instance of an O and a G into their uppercase equivalents. The actual program itself isn't important. What's important is you're sending it data using the triple redirect operator. So, summarizing, you can send data to a process using the input operator, and you can send it an arbitrary string using the actual triple quote literal string input operator. Okay, the final thing that I want to talk about is conditions and loops. So, there are a few loops that you can do in shell scripting, and there are a few conditions that you can do. And these mostly operate around the brackets binaries, and these are actually executables, by the way. If we do rich-a and then run this, we can say it's primarily a shell command, but it's also actually a program, which I think is really cool. And also there's test, which, you know, is also a binary. And these programs are functionally equivalent, and what they allow you to do is they allow you to do conditions in your shell script. So when those initial conditions that we talked about using the or the and are not good enough, you can use the if operator. So, for instance, if you want to check whether a string is 0 in length, so for instance, if dash z, I think it is. For some reason autocomplete isn't working, but if dash z $sign go path, then go path equals dot fi, and we can see, I should just do something that you can actually see on the screen, but you can see this isn't going to work. If I negate it using an exclamation point, we can see that it's going to work, and this is saying if the value of go path is not 0 in length, if in other words, if it's set to something, then run this inside of here. And in reality, obviously, we could actually do this using a one line because it's so small. What you can do is you can do test-z, go path, and then you can do and if test succeeds, if the test we pass to it succeeds and go path is 0 in length, then echo ASDF. If it did not succeed, replace these two with a pipe, then we run ASDF. And this is much more clean and simple on a one line if you just want to do that. You can also run a while loop, which runs using the same kind of conditions as the if does. So for instance, while, and there's not really any good examples you can do this straight away, but while and then some condition, so for instance condition equals 0 or 0, and then what you have to do is you have to do and then echo ASDF, and then at the end you put done, and you can see it's not going to run at all because the variable condition is not 0. If we do condition equals 0 and then run this while loop again, it's going to run infinitely and spam out my terminal. The final kind of loop is for, which allows you to run through files, and this is actually very useful. If we go into our glob directory that we had from before, if we run through and we want to, for instance, concatenate every single, or let's say we want to change the name of every HPP file into just an H file. So first I'm just going to remove all of the H files, but now what we have is a bunch of HPP files that we want to just be .h files. How can we do this? Well, we could try and come up with some solution with globbing, move star.hpp to star.h, but you'll notice this isn't going to work. The auto expand isn't working because this is not valid. There are no H files, so the glob is not going to match anything. There are no HPP files that will match this either because this glob is here. So there's nothing we can do. What we can instead do is we can do for f in, and then what we can show afterwards is a list of files. And so what we can do is we can do star.hpp, and then we put a do here, and anything inside of this loop here will now be run for every file name which matches this glob in f. And so what will is after this in here is just a literal list of things. You can type these out literally in quotes. It can be anything if you really want, but it's most useful for files. And so what we can do is we can do move f, and remember that this f will include the HPP 2, and then what we're going to do is move f to sed. We're going to do sed, and we're going to substitute dot hpp for dot h, and then we're going to pass it in $f, done, and that should read $f. And we can now see that all of those HPP files have been moved to H files. And I've made a slight typo. I didn't include the .h here in the sed script. But what we've done is we've cycled through a lot of files in a directory and we've operated on them. You can also do, for instance, in seqr and then 10, I think it is, and then you can do printf df, and it should just be a string here, and I don't really know what I've done there. That should be a $. There we go. So sequence is going to generate the sequence for us, and I think this actually can be a D, but we need a N here. And what we've done is we've done a sequence from 0 to 10, or from 1 to 10 in this case, and so this is the bash equivalent or the shell equivalent of a very simple for loop. And so you can have any sequence of things here. You can do f in A, B, C, and D. I'm going to have to change this to a string, and it's just going to cycle through A, B, C, and D. And so a for loop will split this along white space, and it will go through each one of the things passed after the in here, placing its value into f for each iteration. Now, this is the third time I've said final thing, but I just thought of one last thing. When we talked about the at operator, this is very simple to another operator, which is the asynchronous start operator. And what this does is it tells a process to start in the background and to stay there. For instance, we run vim at. We can see that vim has started in the background and it got suspended when it attempted to write to the TTY, because obviously we're not seeing the results of it being to the TTY because it's in the background. But you'll notice that when we run vim, we now have a prompt that we can actually do other work with. We can run other commands, we can look at other things in the directory, and if we run fg, we can get this process back into the foreground and we can quit it normally. And you can also run bg, which tells it to continue in the background. In this case, it wouldn't actually work because it would just get suspended again when it tries to write to the terminal, because processes that try to write to the terminal get suspended until you give them their attention. But this is the whole topic of job control, and you can look at what jobs you have running in the background with just jobs. If I run while true do, and I just do done, and then put an at the end, we can see that this is going to run in the background. It's going to take up all my CPU, taking up a bunch of CPU cycles. But if we run jobs, we can see that while true do nothing done is running still. And what we can do is we can do background %1, and it's going to tell us it's already in the background, but say that this wasn't and we just suspended it, we can tell it to continue. And if you have a process that's running, for instance vim, and you press Ctrl Z, what it's going to do is it's going to get suspended. And what you can then do is you can tell it to go into the background, and it's going to attempt to continue it in the background, and then it's going to get suspended when it tries to write to the TTY. And so if we look at our jobs again, we can see that now we have a running process which is infinitely doing nothing, and we have a suspended neovim process. So to get rid of these, what we can do is we can kill, and then the process IDs of each of your running jobs are stored in variables that start with a %sign. So if we kill the process that's running at job 1, that's in brackets here, we run %1, and we have now had this job terminated, and it's going to tell us that job 1 has terminated. If we run jobs, we can see that there's no longer anything running. If we do this again, and instead of doing this asynchronously using the at operator, we instead run it in the foreground. If we press Ctrl Z, for some reason that didn't work. But if this was a real process, we could run Control Z, and it would interrupt the process and it would place it in the background to continue its work. And so I often do this with, for instance, FFmpeg scripts that I have piped out to dev null so that I don't get output spamming my terminal. When you pipe out to /dev/null, it doesn't get suspended for TTY output, and that's a very important distinction to make. But the @ sign is very important for when you want to do asynchronous programming. And so that's the shell, and that's all of the features that I use on a day-to-day basis that I find incredibly useful. And they really make you more efficient when you know how to use them. So, you know, I can run multiple stupid in a row.